In this video we're going to look at implicit differentiation a little bit more. And so in the last video we talked about how to determine whether a function was implicit or explicit, and we talked about how to go about taking the derivative implicitly of a general equation. Okay? So here let's consider the function f of x equaling the inverse sine of x. Okay? So first off, this is a function. It is continuous on its domain, and the limit exists everywhere on its domain, so it should be differentiable. If you look at our basic properties, our product rule, our quotient rule, and our chain rule, doesn't quite work to get our derivative. So we're going to have to use implicit differentiation. Okay? So if I think of y equaling the sine inverse of x, then sine of y is going to equal x. Okay? And if we do it this way, then we can say, by implicit differentiation, we know that cosine of y will equal, cosine of y dy dx will equal 1. And so to simplify this, dy dx will equal 1 over the cosine of y. But we don't want to have y's in there, right? If this is a function of x that we started with, we should be able to end with a function of x just like we did with the implicit functions. So here, let's think about what we've set up there. So if you recall when we evaluated trig functions of kind of arbitrary angles, here y equaling the inverse sine of x says that if I look at the angle y, the sine is going to be x over 1. And so by Pythagorean theorem, we can see that this is going to be 1 minus x squared. Okay? And so if I look at the cosine of y is adjacent over hypotenuse, which says that here, the adjacent over the hypotenuse is going to be the square root of 1 minus x squared over 1. Or the derivative with respect to x of the arcsine of x is going to equal 1 over the square root of 1 minus x squared. Okay. Now just like with our trig functions when we're looking at the chain rule, we can do the same thing here for all of our inverse trig functions using the implicit differentiation. Okay. Now again, some of these are more important that you know than others. And I would say knowing the arcsine, the derivative of that, your arccosine, and your arctangent are the three main ones that you want to know. Okay. So let's look at the arccosine. Okay? So we'll start this the same way. Let's say, again, you can use arccosine or cosine inverse, either one, same function. If I'm looking at the arccosine of x equaling f of x, again, this says that y is the arccosine, or that cosine of y is equal to x. Okay? And so again, by implicit differentiation, this tells us that the negative sine of y, dy dx, is going to equal 1, or dy dx is equal to negative 1 over the sine of y. Again, because of the variable that's our domain variable, we want this in terms of x. So again, we can go back to our triangle. Look at our angle y. So again here, cosine of y we know is going to be x. So here again, cosine is adjacent over hypotenuse, which when we look using our Pythagorean theorem says that the other side is 1 minus x squared. And so looking at the sine of y, we're going to get the opposite over the adjacent. So here, this tells us the derivative with respect to x of our arccosine is going to be negative 1 over the sine of y, which was square root of 1 minus x squared. Similarly, if we look at our arctangent function, we can do the same thing. So y equaling the arctangent of x says that tangent of y will equal x. Taking the derivative implicitly, so derivative of tangent is our secant squared. Okay, so dy dx will equal 1 over our secant squared y. Or if you like, you can think of that as cosine squared of y. Again, looking at our triangle with angle y, tangent is opposite over adjacent, so that has to equal x, which means that our square root here is going to be x squared plus 1. Looking at the secant, it is the hypotenuse over the adjacent, or again, you can think of this as cosine squared, and so it would be 1 over that, and then you've got to flip it. So here, the derivative with respect to x of our arctangent is going to equal 1 over our secant, which again is the square root x squared plus 1. Now notice that secant is squared, so we're going to have to simplify that. And we just get x squared plus 1. Okay, so now let's look at some of the other trig functions. Again, these you don't have to memorize, but it's nice if you know them. If you don't know them, you should be able to derive them just like we're going to do here in a minute. So looking at f of x equally the arcsecant of x, here again we can think y will equal the secant inverse of x. So secant of y will equal x. Okay? Again, using our implicit differentiation, derivative of secant is the secant tangent, and that's going to equal 1. So dividing out by that, dy dx will equal 1 over the secant of y tangent of y. Again, not very pretty. We want to get it back in terms of x. So again, we can go back to our triangle. Looking at our value for y, the secant has to be x, which means the hypotenuse over the adjacent is x over 1, which gives us an x squared minus 1 for the opposite side. Okay. Looking at our triangle, secant of y, again, is just going to be x. That's how we defined it. And tangent of y, we can see is opposite over adjacent, so square root x squared plus 1. Sorry, minus 1. Okay. So our derivative which I'm going to go ahead and leave in the Leibniz notation, the derivative of our inverse secant is going to be 1 over our secant y times our tangent y. So 1 over x times the square root of x squared minus 1. Now if you think back to how we got the cosine and the sine, the nice thing about those were they were basically the same derivative. The only difference was a negative sign. If you think about your secant and cosecant, again, they are very similar functions. The only difference is they are cofunctions of each other. So here, and I will leave this for you to check, if I take my derivative with respect to x of the arc cosecant, this should be negative 1 over x times the square root of x squared minus 1. And again, if I look at my tangent and my cotangent, again, these are cofunctions of each other. So when I look at my derivative for cotangent inverse, the derivative with respect to x should be negative 1 over 1 plus x squared. or x squared plus 1. Okay? And again, I'll leave that for you to check, but you should see that relationship between your functions and your cofunctions. The derivatives turn out to be positive and negative. And we kind of saw that with the graphs of sine and cosine when we did those back in the derivative of trig functions video.